Hi, VC Cap. These are your day 86 notes. On day 86, we're going to learn an extremely important rule that we're going to use really from here on out when evaluating limits that are indeterminate, and it happens to be called L'Hopital's rule. So at the very top, L'Hopital's rule is defined as a way to help us evaluate indeterminate limits. And the most common case that we got that was indeterminate, thinking way back to the beginning of the school year, was something like 0 over 0. That happens a lot. And we have a lot of tricks and ways around getting 0 over 0 and ways that we can still evaluate and determine the limit. But now we have to kind of take these one step further, and there were certain instances where the only way we knew how to do it was graphically and kind of plugging in some values and getting really close, but using the calculator to approximate. We're going to have an algebraic process that will allow us to find indeterminate limits that really look like any of these variety of forms. We're going to look at infinity over infinity today and be able to use L'Hopital's rule to determine the limit. Infinity minus infinity. If you have something of these forms where you have 1 to the infinity, that's going to be a really big case at the end of the lesson. So we're going to start being able to, like I said, uncover a process that would allow us to evaluate limits. But I'm pretty convinced you can probably find these limits on the front page by yourself. Now, usually, I guess at this point in the lesson, I would say, all right, try these. We'll go over them next time. But I want to go over these within the lesson. So I would encourage you to hit pause before I just start showing you my answers. See what you kind of remember from like back to the beginning of the school year of just some basic limit evaluating. Okay, it's probably going to be that you're going to get some indeterminate cases, but I bet you can still evaluate the limits in many of these cases. Okay, so hit pause. I'm about to show you some answers. All right, here we go. Very first one, limit as x goes to 0 of 4x over x. Well, the x's would cancel there, right? We have a removable discontinuity. So the limit as x goes to 0 of 4 is 4. Building from there, the x's would cancel, except we still have 4x left. So now when I take the limit as x goes to 0, still that removable discontinuity at x equals 0. But when I plug in 0 for x, we can evaluate the limit and get 0. Well, when we have these x term that's left on the bottom, right, when I cancel the x top bottom, the limit as x goes to 0 here would not exist. Okay, so we tried, we did some canceling and some simplifying, and turns out that the limit is just non-existent at 0. Now, we could find left-hand and right-hand limits as x approaches 0, but in general, as x approaches 0, the limit does not exist. All right, moving on from there, then we get into some infinity cases. So the limit as x goes to infinity of x squared plus x over 2x squared minus 1. Well, yeah, I mean, x squared plus x, that's going to go to infinity. So is 2x squared minus 1 as x gets bigger and bigger and bigger. But we happen to know that because of some graphical representations, we have an equal heaviness, right? There's a horizontal asymptote that the graph of this function is approaching. So that's why we know the answer in the end is 1/2. Okay, but we'll see today, some algebraic perspective as to how we can justify that as well. All right, and then we get into some weird cases in these examples, infinity minus infinity. Yeah, I mean, n minus n is 0, so I guess that kind of makes sense, but technically that would be a case for infinity minus infinity. Here you start getting into like infinity minus infinity squared, which based on what we know about this function is heading to negative infinity as n gets large, whereas the one at the bottom is heading towards positive infinity. But this whole concept of infinity, I mean, is one infinity bigger than the other? And that's what's crazy, right? Is that you can have this concept of, is infinity squared bigger than infinity? I don't know. Infinity squared, is that bigger than this infinity? I mean, infinity is infinity, right? But we're going to see some very unique cases and some ways that we can get around and still in the end be able to determine the limit. And in upper levels of math, we'll talk about, sort of the cardinality of infinity, okay? And kind of some ranks within infinity, but maybe beyond the scope of our course here. So if we take a look at the next page, let's actually take a look at what L'Hopital's rule says. And this is the first form. So if you look at this section of the textbook, it's defined as being the first form. There's going to be a stronger form that we reference in just a little bit. So here's the conditions. If f of a and g of a equals 0, okay? So that's the case where we get f of a, g of a, if they're both 0, such that the limit is 0 over 0, indeterminate. But f prime and g prime of a exist, and g prime of a is non-zero, then what we know is that the limit as x goes to a of f of x over g of x is equal to the limit as x approaches a of f prime of a over g prime of a. So what we can do to get around this case where we get 0 over 0 is we can take the derivative of the top and bottom. Okay, it's not using the quotient rule. It's the derivative of just what's in the numerator, derivative of what's in the denominator. Plug in that value of a, and if that's not 0 over 0 anymore, then that is the limit. And I can prove to you that that actually does work. So the limit as x goes to a. Let's talk about the statement right here. The limit as x goes to a of f prime of a over g prime of a, according to the definition of derivative, would be the following. Well, the top for the definition of derivative would be the limit as x approaches a of f of x minus f of a over x minus a. All right, so this would be the slope of a secant line, but as x approaches a, we're approaching the slope of the tangent line. And similarly, in the denominator, you get limit as x approaches a of g of x minus g of a over x minus a. So we're going to do a couple things in the next step. One being, if you think about multiplying kind of the top and bottom here by x minus a, those x minus a's will go away. And then kind of sucking this back into one limit, we would get the limit as x approaches a of up here f of x minus f of a. And on the bottom, g of x minus g of a. Well, here's kind of the critical step. From the initial condition, we know that f of a and g of a are both equal to 0. So since I'm subtracting 0 from both of these, we've just proven that the limit as x approaches a for f of x over g of x is equivalent to the limit as x goes to a of f prime of a over g prime of a. So thus proving L'Hopital's rule that if we get 0 over 0 here, when I plug in a for the original function on the top and bottom, we can then take the derivative at a on the top bottom, evaluate the limit, and that would be equivalent, which I think is pretty fantastic. Let's go to an example that we should know how to do without L'Hopital's rule, but let's apply it and see what happens. So when I plug in 2, the first thing you really have to check is, do I get that indeterminate form? Because if it's not indeterminate, L'Hopital's will not apply. So 2 squared minus 4 on top, yep, 4 minus 4 is 0, 2 minus 2 on the bottom is 0. So based on what we just proved up here, we can take the limit as x approaches 2 of derivative of the top is 2x. The derivative of the bottom is 1. Okay, great. Plug in the 2 for x. 2 times 2 is 4. Boy, was that easy. Now, the alternative to this method is what we would have done at the beginning of the year, where you would have said, all right, if I can factor cancel, maybe I'll be able to evaluate the limit, right? This has a removable discontinuity at x equals 2 when I cancel those x minus 2's. So, of course, this is still a valid technique, but what we'll find is that L'Hopital's rule is really effective in situations where maybe we can't do this easy factor cancel business. But if I plug in 2 there, yeah, of course we are going to get 4 as well. All right, limit as x goes to 0 of sine x over x. Boy, isn't that our WFL? WFL, remember what that means? World famous limit. Boy, this comes up quite a bit, especially at the beginning of our course. The limit as x goes to 0, we proved in the very beginning of our school year, of sine x over x equals 1. And the reason why we proved that is according to the squeeze or sandwich theorem, and we had some nice diagrams to kind of help us justify that. But what would happen for L'Hopital? Well, this is a 0 over 0 case, right? So if I apply L'Hopital's rule, it would be the limit as x goes to 0 of derivative of the top is cosine x, derivative of the bottom is 1, and hey, cosine of 0 is 1. Boy, if only we knew L'Hopital's in the very beginning, that would have made this limit so much easier. But we really needed to build towards L'Hopital's rule. Okay, so we couldn't introduce it that early on and just use it, without knowing kind of the process behind. And we're going to get to a great limit at the end that you're going to be so excited about. It's coming. Okay, so for this last one, if I plug in 0 for x on the top and bottom, do we get 0 over 0? Well, actually, turns out the answer to that is no. If if I plug in 0 for these x's, you get -4 over -2, which is +2. So I don't want you to look at something that's fractional and assume that it's 0 over 0, right? You still want to make sure you're plugging in, seeing if it's indeterminate, and if so, we proceed. Because L'Hopital won't work if it's not 0 over 0. Look what happens. If you find the derivative of the top and bottom and try and use L'Hopital, derivative of the top is 6, derivative of the bottom is 12, so now all of a sudden you're getting 1/2. So L'Hopital is only applicable when the function on the top at A equals the function on the bottom at A, which is 0. So in other words, you're getting that indeterminate form. Okay, so you want to make sure that before you just go ahead and start finding some derivatives, because you're really excited, that we actually think carefully about plugging the value in that limit that the x value is approaching. Once we do that, if we get 0 over 0, then we can go ahead and apply L'Hopital. All right, moving on to the next page. So the stronger form is on page 569 in the textbook. And if you read through it, it looks like it says essentially the same thing. Instead of saying x goes to A, they say it's the limit as x approaches x sub 0 for f of x over g of x equals the limit as x approaches x sub 0 for f prime over g prime. So again, kind of the same type of idea here, but the stronger form of L'Hopital's rule is important because what it states additionally is that you can apply the process again and again and again and again, however much you need, until we get something that's not indeterminate. So it's very possible that when you're doing L'Hopital's rule that you apply and find the derivative of the top, derivative of the bottom, you plug in the value that x is approaching for your limit, and you find that it's still 0 over 0. So essentially what the stronger form states is that if you get 0 over 0 again, have no fear, you can do it again. Find the next derivative. And if you get 0 over 0, do it again. And go again and again and again and again until you don't get 0 over 0 anymore. And you're able to make a determination. So let's start in this example right away, just making sure that this is indeterminate and that L'Hopital's rule would apply. So if I plug in 0 here, we're going to get radical 1 minus 1, which is 0. 0 up there. Yep, we definitely get 0 on the top when I plug in 0 for the x's. 0 squared, of course, is 0. So it looks like we're up to the stage where we can find the derivative of the top, derivative of the bottom, and check to see what's going on there. Limit as x goes to 0 of radical 1 plus x would be 1/2 times 1 plus x to the negative 1/2. I'll leave it as negative exponents just so I don't get something that looks too complex fraction-ish here. And the derivative of the inside is just 1 with chain rule, so we don't have to worry about that. Derivative of negative 1 is 0, and then at the end you're going to get minus 1/2. In the denominator, we get 2x for the derivative. So now that I have the derivative of the top and bottom set, when I plug in 0, I know I definitely get 0 on the bottom, which does not necessarily mean we're going to get 0 over 0, but let's check it out. If I plug in 0 up here, you get 1 to the negative 1/2, which is 1. Half of 1 is a half. Yep, half minus half is 0. So go again. That's what the stronger form of L'Hopital states. You can keep going. Find the derivative of the top, find the derivative of the bottom, and see what happens if we try again. So the derivative of the top now is negative 1/2 times 1/2 is going to be a negative 1/4 out front. 1 plus x to the 1 less there would be negative 3/2 power. Derivative of the constant is 0, and the denominator is just a 2 now. Okay, so I definitely like the denominator where it's at. 2 derivatives later, now it's just a constant. So it's something over 2. What happens when I plug in 0 for x here? 1 to the negative 3/2 is 1. 1 times negative 1/4 is negative 1/4. And negative 1/4 divided by 2 is negative 1/8. Done. So for something like this, if we think back to the beginning of the year, I don't think we would have had a good algebraic strategy to manipulate this to wind up getting negative 1/8. So what would we have done? Probably the calculator, right? Either look at the graph or go to the table and get really, really close to 0 and hope that I can recognize that it's approaching negative 1/8. but now we have a great way to be able to determine algebraically that limit. And what's great in addition to this is that L'Hopital also applies for infinity over infinity. Okay. So if f of x and g of x go to infinity as x approaches a, then the limit as x approaches a for f of x over g of x would equal the limit as x approaches a of f prime of a over g prime of a as well. So just stating that it doesn't have to be 0 over 0 as your indeterminate case. We would also consider infinity over infinity to be indeterminate as well. So there's an example just like it at the top of the next page. So limit as x goes to infinity of x squared plus x over 3x squared plus 1. Certainly, as x gets larger and larger, the top is going to get larger and larger. Same thing for the bottom. So you get infinity over infinity to start. So I don't know. Let's go ahead and use L'Hopital's rule. Limit as x goes to infinity of derivative of the top would be 2x plus 1. Bottom would be 6x. So if I plug in x as x goes to infinity, top is infinity, bottom is infinity. Okay, didn't really help me the first time, so we can go again. Limit as x goes to infinity of, well, now we have 2 over 6. So we reduce it down to these constants. We eventually break this down to know that the limit as x approaches infinity is 1/3. Now, maybe we didn't need L'Hopital's to do this because we know something about the way this graph looks, and we know it's the ratio of those coefficients because we know something about horizontal asymptotes, okay? But moving on from here, we want to start looking for these two forms. We want to look for infinity over infinity, or we want 0 over 0. Those are the two indeterminate forms that we can apply L'Hopital's rules in. So here's a different indeterminate form. So limit as x approaches 0 from the right of 1 over sine x. So as we approach 0 from the right, this fraction is going to get larger and larger and larger and larger. So that's going to be infinity. Same thing for 1 over x. That's going to get larger and larger and larger as well. So we get this infinity minus infinity case. So if we're not quite sure what that would turn out to be in the end, what we're looking to do is convert to get a 0 over 0 case or an infinity over infinity case. If we can do one of those conversions, then we can apply L'Hopital's rule and hopefully evaluate the limit there. So if I were to get this into one fraction, that's what I'm going to do is kind of a trick here. Limit as x goes to 0 from the right of, it would be x minus sine x over the common denominator x sine x. When you take the limit as x approaches 0 from the right, you're going to get 0 minus 0 on top and 0 times 0 on the bottom. So we get 0 over 0 once you make this into a single fraction. So now that we have that, let's apply L'Hopital's rule. So the first step I would do is take the limit as x approaches 0 from the right of the derivative of the top. So that's going to be 1 minus derivative of sinus cos. And then over the derivative of the bottom, you need a little product rule there. 1 times sine x would be sine x plus the derivative of sine is cos. That's going to be an x cosine x there. All right, so then when I plug in 0, we get 1 minus cos of 0. Cos of 0 is 1, so 1 minus 1 on top is 0. Doesn't mean it's definitely going to be 0 over 0, but let's see what happens on the bottom. We get sine of 0, which is 0, plus 0 times something. Okay, so we get 0 over 0 again. All right, let's keep going. Limit as x goes to 0 from the right of, find the derivative of the top. That's a constant. Derivative of negative cos x is sine x. Derivative of the bottom, well, let's see, we get cos x here. Plus, then we have to do product rule there. So that's going to be 1 times cos plus derivative of cos is negative sine times x. So it's going to be negative x sine x. All right. I know I can combine some like terms here, but let's just start plugging in 0, see what happens. Sine of 0 is 0. All right. Cos of 0 plus cos of 0, that's 1 plus 1 plus, even though this is going to turn out to 0, it's not going to be 0 over 0 anymore. It's going to be 0 over 2, which we know in the end would have a limit of 0. So we have to go through a few iterations to get there, but here's the algebraic proof that even though infinity minus infinity seems like it should just be 0, here's the justification as to why using L'Hopital's rule. Okay. So the trick here was just to make it into one fraction. What I'll tell you for something like this one right here is that it's not always easy to do that quick conversion. Try to get 0 over 0 or infinity over infinity. In fact, as x goes to infinity here, if I look at this product, x times sine of 1 over x, this would be infinity times 0, right? As x gets bigger and bigger and bigger here, 1 over that large quantity is getting really tiny, and sine of that tiny value is going to be 0. So this one actually needs a slightly different trick. It's not going to wind up necessarily using L'Hopital. This could have been a limit that we calculated in the beginning of the year by doing this trick. Let y equal 1 over x. And although we're taking the limit as x goes to infinity, if I make this substitution, as x gets bigger and bigger, we know that y is getting closer to 0. So rather than approaching this from limit as x goes to infinity, it's going to be the limit as y approaches 0 of, and I guess technically we should say 0 from the right. Since as x goes to infinity, that would be 0 from the right. Okay. So let's see. I have to replace x. What is x really equal to? X is really equal to 1 over y. Okay, if we get x alone in this substitution, that's 1 over y. 1 over x is y, though, so that's sine of y. And you see where this is headed? So it's the limit as y approaches 0 for sine of y over y. World famous limit of 1. Now, at this point, if you had forgotten that for some strange reason, we could apply L'Hopital at that stage in the game, right? When we get 0 over 0. But because this is so familiar to us, I hope that you would just jump to the conclusion of saying that's 1. But we had to get a little sneaky here. You had to use that substitution to be able to evaluate this limit. Okay? Otherwise, it wasn't, I think, an obvious example of getting a 0 over 0 case right away. Okay, moving on from here. What about these cases? 1 to the infinity, 0 to the 0, or infinity to the 0? What's going to happen in those instances? We're still trying to look to build 0 over 0 or infinity over infinity. So if you look at this first case, as x goes to infinity, this might look familiar to you. You might even know what the answer is based on looking back in the, I don't know, a couple lessons ago. But if you don't remember, I'm going to justify it for you right now. As x gets bigger and bigger, this is going to 0, right? So you get 1 plus 0. And then let's see, as x gets bigger and bigger, that's going to infinity. So this is like 1 to the infinity. And you look at that and you think, well, I don't know, 1 to the infinity seems like it should be 1, right? 1 to a power 1. But that's actually not the answer. And the way we're going to approach this is let's let y equal the quantity 1 plus 1 over x to the x. And then from there, what I'm going to do is do our ever famous trick of taking the natural log of both sides. So bring that x out front. Now here's what I want to do. I want to eventually apply this limit as x goes to infinity to this quantity. However, we want to write this as some sort of quotient. So I get that 0 over 0 case or that infinity over infinity case. So instead of rewriting this as multiplying by x, we're going to rewrite the multiplying by x as dividing by 1 over x. Now that's a really sneaky trick. But that sneaky trick allows us to be able to take the limit as x goes to infinity and apply L'Hopital's rule. You'll see why in just a second. So right now we have the ln of y would equal the equivalent form ln of 1 plus 1 over x divided by 1 over x, right? Multiply top and bottom by x, you get back to where we were just a second ago. All right, if I do that sneaky trick, let's take the limit as x approaches infinity of this quantity, ln 1 plus 1 over x over 1 over x. Well, as x goes to infinity, we know that this goes to 0, so ln of 1 plus 0 is ln of 1. And the bottom as x goes to infinity, that's heading to 0. Oh, by the way, ln of 1 is 0, so we do get indeterminate 0 over 0. Let's apply L'Hopital, see what happens. Limit as x goes to infinity of the derivative of the top. Well, derivative of natural log would be 1 over 1 plus 1 over x times the derivative of the inside, which is 1 over x. Well, the derivative of 1 over x is negative 1 over x squared. Keep in mind, you're going to find that same exact derivative in the denominator. This would be negative 1 over x squared. So notice how those are going to cancel out, and we're taking the limit as x goes to infinity of 1 over 1 plus 1 over x. So what is the limit as x goes to infinity here? Well, this is going to go as x goes to infinity. This goes to 0. So we get 1 over 1 plus 0, which is 1. Now keep in mind, this is what ln of y equaled. So bring it on back down. If the ln of y is equal to 1, then y is equal to e to the first. So if the limit as x goes to infinity of my quantity y, which by the way, y was 1 plus 1 over x to the x, we've just justified and proven, So we've just proven here that this limit is truly e. We just kind of accepted it and we talked about it a little bit. We defined e in this fashion, but here is the justification. We had to wait a little bit. We had to get L'Hopital. We had to know the derivative of some natural log functions, right? We had to really build towards this. That is the definition of e. That is why the limit as x goes to infinity of 1 plus 1 over x to the x is e. What I'll do is I'll save these next two for tomorrow in class, but if you're curious about trying them, this is from the December review. This is a question that you would have had to do probably just by analyzing it graphically, but now you should have the skills to do this. Use a very similar approach. Let y equal 1 minus 1 over x to the x, ln both sides. See if you can figure out what this equals. And then we're going to generalize it to what if this is just n over x? We're going to build that case. So I'll save those two examples for tomorrow. And once we go over those two cases, then I'll have you try these for practice in class. So we've got some AP style questions. Here's a chart with some values given for f and f prime, g and g prime. You'll answer some multiple choice. And then a great question from 1980, good old year. I wasn't even born yet. Okay, about an acceleration that you're given, and we'll read through that tomorrow. I'll give you some time to see how far you can get with that one as well. Okay, that is it for L'Hopital's rule. I think it's a great introduction. There's going to be more to come with it. Okay, so have no fear if you think you still need some more practice. Have a great rest of your day.